Hello everyone, and welcome to this lesson for grade 12 physics for Masait Boarding Secondary School. The topic we are dealing with is electromagnetic induction under electricity, and I'm your presenter, Mr. Nkumbi A. And I hope that you are keeping safe, you are observing hygiene, washing your hands regularly, and also masking up in public and avoiding visiting anyhow, because we wish to see you soon. Okay, as you come back. All right, so in this lesson, the following are our outcomes. We will investigate the phenomenon of electromagnetic induction. Then we shall describe the factors affecting magnitude of EMF produced during electromagnetic induction. Then we shall also state the direction of EMF produced by an induced, we shall state the direction of current produced by an EMF, by an induced EMF, sorry. Okay, so these are the three outcomes for our lesson today. So let's go straight into our first outcome, looking at investigating the phenomenon of electromagnetic induction. Okay, so we want to know exactly what is electromagnetic induction, this phenomenon of electromagnetic induction. What is it? So to understand fully, I'll give you a scenario here. So if we have a magnet, if we put a wire between the two poles of a magnet, the north and south, we can imagine this is one magnet with which is a U-shaped magnet, or we can just think that these are two different magnets, but this is the north and this is the south of two different magnets. So we understand that if that's the case, then the magnetic field lines are originating from the north and entering into the south of the other magnet. So if we put a wire between them and then we connect it using small wires to a galvanometer like this one. Remember, a galvanometer is a sensitive meter. It can detect very small current flowing through a circuit. So if we keep on moving this wire up and down so that it is cutting the magnetic flux here. So each time it cuts the magnetic flux, we see the galvanometer deflecting. By the way, a galvanometer has a zero in the center, and it has negative values and positive values on the other side. Negative here, positive on the other side. So when you move the wire up and down, this conductor here, you will see the deflection of the galvanometer in different directions. So from here, what we see is that when the moving conductor cuts across a magnetic flux, the galvanometer deflects. The point of the galvanometer deflects. Now this induces, the deflection of the point of the galvanometer indicates to us that there is current flowing in the conductor because of the movement that we are making. Now this phenomenon is what we call electromagnetic induction. Basically, in trying to describe what electromagnetic induction, that's what we can say. But if we were asked to state what electromagnetic induction is, then we can say electromagnetic induction is the production of an EMF across a circuit because the circuit or the conductor cuts through a magnetic flux. So magnetic flux is actually a group of magnetic field lines. So when I say magnetic flux, I'm referring to a group of magnetic field lines. So we can say electromagnetic induction is the production of an EMF across a conductor because this conductor is cutting across magnetic flux. So it has to cut, so it has to keep on moving. If it is stationary, then it is not cutting. To understand better or to have a deeper understanding, we shall actually do a demonstration. Okay. So the next factor we wanted, the next outcome we had was to look at factors affecting the magnitude of the EMF produced. Remember, we have said when that conductor is cutting the magnetic flux, an EMF is induced. Now, how will the size of the EMF produced be increased, or how can it be reduced? So what factors actually affect the size of the magnitude of the induced EMF? Magnitude simply means size. And the factors affecting the size of an induced EMF are summarized in what we call Faraday's law of electromagnetic induction. So the factors affecting the size of induced EMF are: 1, the speed of either magnet or coil. Remember, you can either be moving the coil. This is another arrangement. You can be moving the magnet towards the coil and withdraw it, so you can be moving it to and fro, or you can hold the magnet stationary and instead move the coil to and fro the magnet, so that there is cutting of this magnetic flux by the conductor making up the coil. And in this case, you'll see that the voltmeter with a 0 in the center will be showing some deflection. So the factors affecting the size or magnitude of induced EMF are: 1, speed. If we move it rapidly, then the size of the induced EMF will increase. If we reduce the speed, the size will reduce. Strength of magnet. If we use a stronger magnet, then more flux will be cut and the EMF produced will increase. If we use a magnet that is weak, then even the voltage or the EMF produced will also be reduced. Then the other factor is the number of turns of the coil. So you can see here this coil has 15 turns here. So if we reduce the number of turns, the voltage or the EMF induced in the coil will reduce. If we increase, then there is increase in the voltage. So those are the 3 factors affecting the size of induced EMF. But then let us look at how we can demonstrate that. So what I have talked about will be demonstrated in the next clip. So pay attention and look at how the 2 factors, that is number of turns and the speed of motion, will be demonstrated in the next clip. Unfortunately, I'm unable to show you change in strength of a magnet, but at least I have told you that increase in strength of a magnet results into increased EMF. Okay, so please pay attention and look at this clip here. Okay, so in this demonstration, we're going to look at how an EMF is produced when the magnetic field of a magnet cuts across a coil, or when a conductor cuts across a magnetic field. So in this arrangement, you can see here there is a coil here with the 5 turns, as you can see, and it's the 2 terminals the 2 ends of the coil are connected to the terminals of a voltmeter, so that it can help us to actually measure the voltage that we have that is being produced from the coil. Now we have said that electromagnetic induction happens when the magnetic fields cut across a coil. So across a conductor. So in order to demonstrate the cutting, the magnet should be moving. Okay, so I'll be moving this magnet towards and away from the coil, and you can see that this voltmeter has a 0 in the center. Okay, so when the magnet is stationary, the pointer is at 0, meaning there is no voltage being produced. So let's try. So when I move the magnet towards, you can see there is a small deflection of the needle of the galvanometer or the pointer, and you can see the direction of the current being produced. Okay, so when I take it away, when I take it towards and when I take it away, the direction is changing. Okay, and you can see that if I increase the speed of motion of the magnet, the voltage produced is also increasing. Okay, now this time let me increase the number of turns of the coil. So let's increase the number of turns. We go to at first we had 5 turns. This time I've taken it to 15 turns, and you can see that the voltage, you can see how far the galvanometer, the pointer of the voltmeter is going. It's almost reaching the ends of the voltmeter in both directions. So if I increase the speed, you can see how the voltage produced is increasing. So the current being produced in this case has no one particular direction, because when I take the magnet in this direction and in that direction, there is change in direction of deflection. It means current is being produced is also alternating, it's changing direction. So the type of current being produced is alternating current. So basically what we can see here is that the induced EMF increases when the number of turns is increased, and also when the speed of rotation, of motion of the magnet is increased. All right, so I believe that you have understood the concept from there. The talking about factors affecting the size of EMF produced, or the magnitude. So we go to our last part. I'm sure that's outcome number 3, which is talking about state the direction of current produced by an EMF. Okay, so sorry for that. So the direction of current produced by an induced EMF can be determined by using Lenz's law in combination with Fleming's right-hand rule. Now the right-hand rule already we covered it when we were looking at the magnetic effect of an electric current, where we used the right hand, the thumb representing the direction of the North Pole, and the fingers in the direction they are curling. That's the direction in which current is moving. Okay, so the only thing I need to introduce, which is new here, is Lenz's law. Okay, now according to Lenz's law, the direction of current induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes the initial changing magnetic field. Now you don't need to be confused by this law. You can go it a number of times. I don't want you to memorize it. I want you to understand it. What this simply means is that when you are bringing when a magnet is approaching a coil like this, okay, now if it is approaching, you expect if this coil also starts behaving as a magnet, because there is an induced EMF and the current is moving around it, through it, if this magnet is to go towards it, then it means that there should be a south pole here, so that this is attraction. Okay, a magnet moving towards another magnet, that's attraction. So there should be a south pole here, but unfortunately it doesn't happen that way. That's where we are saying it opposes the initial changing magnetic field. This is not true. I mean, this is not the normal case. A north cannot be attracted by a north, but instead this is what happens. So when a magnet is moving towards a coil, a north is developed here, and when you withdraw it, a south is created. Okay, now that will help you to tell the direction of current, because the arrows indicating current here in exam questions, you will not see them. But once you realize that when a magnet, the north moves towards a coil, a north is produced here, then using Fleming's right hand rule, you can tell the direction in which current is moving. So in this particular case, it is in this direction. So from here you can see a magnet moving towards a coil with its south pole approaching, and the south develops here. This movement is against the repulsion. Okay, it's against repulsion, because we know a south and the south are supposed to repel, but instead this is a south and this is a south, but they are moving towards each other. So this movement is against repulsion. Okay, so using Fleming's right hand rule again, you can tell the direction in which current is moving. Here, movement of the coil is against attraction. When you withdraw if a north pole develops here and the south pole develops here, these two are supposed to attract, but instead that's when the magnet is being taken away. So this movement is against attraction. Again, once we understand that when a south is moving away, a north develops here, then that can help us in combination with the Fleming's right hand rule. Where the north is, that's where the thumb will point. So it means here current is moving up. When you grip this with a curling of fingers, the fingers will curl in that direction. So current is moving like this. So basically this is how you can tell the direction in which current is moving. For you to be able to remember this, you have to use Fleming's right hand rule. You shouldn't forget it, and you should use Fleming's law, which states that the developed magnetic field, the induced current develops a pole that opposes actually the movement that is producing it. It produces a south here, but that's when the magnet is moving towards, instead of producing a north, so that there is attraction. But when a south approaches, a south develops. When a south is taken away, a north develops. When a north approaches, a north develops here. Okay, you can see here there is a south, so it means there is a north here. Okay, so these are the concepts that I wanted us to look at, bringing us to actually the end of our lesson. And with this, we can now look at an exercise that I have prepared for you. Remember, what we have looked at here is the foundation of what we'll be looking at. We'll be looking at an AC generator, and then we'll go to DC generator for those who are doing pure science. So please make sure that you understand these principles we have looked at, and then we apply them when we'll be looking at an AC generator, because actually an AC generator uses the principle of electromagnetic induction. So here is your exercise. Question 1, what is electromagnetic induction? So you have to explain what electromagnetic induction is. Then we go to the second question. When a magnet was pushed towards a solenoid, the sensitive meter connected to the solenoid deflected to the right. So you can see this arrangement here. When a magnet was pushed towards the coil, then the sensitive meter shows a deflection to the right. So first question is, when the same magnet was pulled away from the solenoid at the same speed, now it is being withdrawn, what was the deflection on the meter? So you answer that question. Then the last one, state 3 ways in which you can increase the EMF produced. Okay, so this is your exercise. Do the work. If you are to hand in your work, do not post it on the group, inbox it. Send to my WhatsApp line so that I can mark your work. Thank you so much. Hope to see you in the next lesson, which will be about an AC generator. Please remember to keep safe and share these lessons with others who may need them. Thank you.